In this video, I'll introduce filtered back projection or FBP. This is the most popular analytical reconstruction method. It can only be used for 2D parallel beam projection geometries, but for other geometries similar techniques exist, which is the topic for a future video. Now in this video, I'll explain how the algorithm works, and then in a future video, I'll explain why it works by deriving it from the Fourier slice theorem. Now as you can tell by its name, FBP involves two phases, a filtering and a back projection phase. We'll firstly discuss the back projection. This operation, more or less, resembles the inverse operation of a forward projection. But instead of each detector getting the line integral of the object function, now each point on the object domain receives the value of the detector point where it projects to. So in essence, the detector function is smeared out over the object domain. This is then done over all projection angles, summing up the values from each direction. So let's look at an example. If we back project from one direction, you indeed get the detector function smeared out over the volume. If we then add the back projection of a second direction, two of such smears are added together. For 8 projections, 8 smears are added together, and you can already start to see the outline of the object that we're interested in. And as more projections are back projected, this object becomes clearer and clearer. However, it never really becomes totally sharp. And there is a good reason for this. Remember the Fourier slice theorem, where we noted that with the tomographic setup of acquiring projections, the Fourier domain of the object is sampled in such a way that the low frequencies are sampled much more densely than the high frequencies. The result of that is exactly why the back projections appear to be so blurry. Because in image processing, the low frequencies take care of the smooth surfaces, and the high frequencies take care of the details and the sharp edges. And because the high frequencies are underrepresented here, the resulting back projection is indeed severely unsharp. But no worries, because we haven't touched on the second, well actually the first part of the FBP algorithm, namely the filtering. The idea is that by applying a high-pass filter on the detector function, the low frequencies will be suppressed such that they will not result in an overly blurred back-projected image. Now, as is typical in signal processing, the filter on the detector function is applied in its Fourier domain. So first, this function is Fourier transformed using the fast Fourier transform method. The resulting spectrum is then filtered by multiplying it with what is called a Ramlack filter. You can clearly see that by doing so, the low frequencies are somewhat suppressed and that the high frequencies gain relative importance. Also note that at some point there is a cutoff and all frequencies higher than that are set to 0. This is to reduce noise in the reconstructed image. Now after this filtering, the spectrum is inverse Fourier transformed, resulting in a new detector function, which we'll call Q, and in FBP, this is then the function that is subsequently back projected over the domain. So if we look at it from a mathematical perspective, for normal back projection we get the smearing out of a detector function over the lines of the X-rays, but for FBP we do this back projection on this filtered detector function Q, which is inverse Fourier transform of the Fourier transform of the original function P, multiplied then with the absolute value of omega, which is then the Ramlack filter. Now going back to our example, if we back project one filtered detector function, we get an image where basically only the edges are visible or are smeared out. If we then do this for more projection angles and sum them all up, you do eventually get a nice and sharp reconstruction.